Hi, I'd like to thank the organizers for giving us the opportunity to talk about our latest work on p-bits. Now, this is some work that we've been doing for the last couple of years, and today I'd like to give you a little bit of an overview and some of the latest results that we obtained using p-bits. So let me begin by talking about computation today. Now, as you all know, most of our digital compute is based on the idea of the bit, which is really a deterministic 0 or 1. And these bits are represented by our transistors that we've scaled up to billions and billions of units in these chips that we built, such as CPUs, GPUs, and even lately, these specialized application-specific chips like tensor processing units that are called TPUs. Now, on the other extreme, on some spectrum, you might say that there's the qubit, which is really this interesting object, which is a superposition of zeros and ones, okay? And that's a technical thing to describe, but there's a lot of effort in trying to build quantum computers with qubits, and there's lots of major players in the space. There's Google, lots of startups, and people are trying to build these quantum mechanical computers which operate on these different principles which would allow complicated problems to be solved by these qubits. Now, both of these domains are approaching towards domain specificity. What I mean by that is, in the case of bits, you see a lot of effort in trying to accelerate some of the difficult computational tasks of machine learning. On the other hand, quantum computing is also similar, that quantum computers are not expected to completely replace our existing computers, but they are really good at some natural tasks that come naturally to quantum computers. And these include simulating quantum mechanics itself. And this was the original idea that was proposed by Richard Feynman back in 1982. So in a lot of senses, these bits and qubits are becoming domain specific. So we're really living in the area of this domain specific hardware. Now, today I'll tell you a little bit about these p-bits, which are really in between bits and qubits, okay? That they're not quantum mechanical or coherent, but they really are not like your deterministic bits either. They are these probabilistic objects which fluctuate between this logic 0 and logic 1. And p-bits also are domain specific, and they are connected, very well connected to some of the machine learning models, especially statistical mechanics-based machine learning models, and they also share a wide application space with qubits, and especially the NISQ era quantum computers are really all about applications that can be targeted by p-bits as well. Now, let me give you a brief introduction. Now, a p-bit in machine learning language is a hardware binary stochastic neuron. And what is a binary stochastic neuron? Well, it's just this three-terminal device where we don't show the power lines here. You have an analog input and a digital output. And the analog input controls the output of the digital output so that you get a different probability of outputting a 0 or 1 depending on the analog input. So if the analog input is 0, you see this fluctuations between +1 and -1. And if you take a time average, you see that these +1s and -1s, despite being random, come in with the same probability. Now, the analog input controls this duty cycle. So you can, at any point, you can change this analog input to change the probability of obtaining a +1 or a -1 or a 0 or 1. These are interchangeable. Now, if you swept this input in the background, then you would see something like the blue curve here, where we sweep the analog input, it's stuck to -1 in the beginning, and then it fluctuates, and then it gets stuck to +1, okay? And if you sit at any one of those points and take an average, we design the p-bit so as to give this sigmoidal or hyperbolic tangent-like shape, which is this S shape that is common in a lot of these neural networks, okay? And mathematically, you write it like this, that you say that I'm taking the sign of a number that's being compared to a random number that's changing between -1 and 1, and depending on the analog input, you get these different probabilities. Okay, that's really simple. Now, how do you build a p-computer out of this. So this is the building block for the p-bit. Now, to build a p-computer, you need to interconnect many of these p-bits. They need to talk to each other to do something useful, okay? And that's achieved by this architecture where we have these n of these p-bits, and they interact by what we call a synapse or a wait logic, where you take the outputs of these digital p-bits, you get a combination, or you get this linear combination of their outputs, and then produce an input for each of these p-bits. Okay, so that's one of the simplest feedbacks that you can do with, linear combinations. Though I must mention that this is only a special case. You could have more complicated feedback mechanisms for much more general problems. But this is what you might call the icing problem, where there's a lot of activity, ongoing activity to try to solve these icing problems. But in general, the architecture we envision is a little bit more general. Okay. Now, this is interesting because, unlike many digital circuits and architectures where you have a clock, this system doesn't need to be clocked. Okay. That's a very different, that makes this architecture very different from our usual digital computers, because it's clockless, this circuit can operate as a massively parallel unit, that the more you put in the p-bits into this, the more parallel and efficient it gets. And I'm going to talk about that later. Now, an important requirement, though, is that this requires fast interconnection. Okay, that now for me to explain it, if you look at this architecture on the top right, you see that there are these two time constants, which we call tau p-bit and tau synapse. Now, the tau synapse is the time it takes for you to generate an input given the outputs, and tau p-bit is the time it takes to generate an output given the inputs. Now, this communication needs to be fast or relatively close to your p-bit fluctuations, because you might imagine that if the p-bit is fluctuating and before it fluctuates again, you need to communicate that information to its neighbors. Otherwise, it becomes cacophonic, that it doesn't work and it doesn't get to the right distributions. Okay, so these are the technical details, but really that this architecture that you're seeing here is really the key architecture, because you can do all of the examples and applications that I'll show shortly really comes about using an architecture like this. Okay, so what are the application spaces of p-bits? Let me briefly mention some of these application spaces. And in the beginning, I mentioned there are these quantum-inspired applications and then machine learning-inspired applications. And in technical terms, much of the quantum-inspired application seems to fall under the category of solving optimization problems, whereas in machine learning and AI, it turns out you need to sample these from these high-dimensional probability distributions. And the central idea of this talk is that p-bits can provide hardware acceleration, very useful acceleration for these wide variety of applications. So one very interesting paradigm that we invented, inspired by other work and computer science ideas, was this idea of invertible logic. Okay, and invertible logic is a little bit like Boolean logic, like you design a digital Boolean circuit, but then if you do it with p-bits, you can operate the circuit in reverse. So what that means is if you have a binary multiplier, you can really operate it in reverse to solve the factorization problem. And I'll show examples of this very interesting concept. Now, combinatorial optimization problems are really these fundamentally difficult problems in computer science. And the most famous one perhaps is the traveling salesman problem, where you try to visit n cities exactly once while trying to minimize distance. Now, these problems often have powerful probabilistic algorithms. And it turns out whenever you have a naturally probabilistic problem, p-bits become a natural p-bits become a natural substrate to solve these problems. And intriguingly, quantum systems and probabilistic systems are closely related. In fact, a good number of quantum systems, such as the one that D-Wave is pushing, for example, can be emulated by p-bits. And this is this rather intriguing idea that's been known to condensed matter physicists and the Monte Carlo simulation experts. But here, what we've explored and revealed was that you can use these arrays of p-bits and really solve some of these quantum problems like the D-Wave is proposing to solve. And there is Bayesian networks in machine learning and AI, very briefly, that you have these probabilistic networks where there is this causality or there is this hierarchy of nodes which probabilistically affect their children. And it turns out inferencing, or really figuring out what this circuit is trying to tell you, is a computationally difficult problem, which can also benefit from hardware acceleration from qubits. And in machine learning, there's the related, much more difficult problem of learning, and that's also a natural application space for qubits. Okay, this is this very deep area of Boltzmann machines and how you learn a Boltzmann machine using qubits. And we have work on all of these. We have been working on this area for a number of years, and if you're interested, you can check these papers out to see how the comparisons are done and how you're doing solving these problems with qubits. But that's really the main idea, that whenever you have a naturally probabilistic application, qubits become really a good, useful fit to those applications. Now, how do you build a qubit in hardware? Now, this has a lot of answers and a lot of ways to do it, because unlike a qubit, you don't need the quantum coherence. So there's a lot of ways to come up with a qubit implementation, and we're exploring several of these at the same time. But one really compact and hardware physics inspired approach is based on magnets. And let me quickly tell you what that is. Now, this is the building block that we're trying to get, remember. Now, if you remember the physics of this freshman physics of magnets, a magnet is really this object that can be in these one of these two states, red or blue, or up or down, north, south, that's separated by an energy barrier, something of the order of 40 or 60 kT. Now, if you leave a magnet in one of these states in the presence of thermal noise, which has energy equivalents of around a kT or so, it turns out the magnet tends to stay in one of these energy wells, okay? And the way to understand how this noise behaves is tau is the retention time, or the time it takes for the magnet to kind of stay in its current state. That's given by an exponential related to the energy barrier, okay? And there's a time constant that's out front, and for magnets that's around picoseconds or nanoseconds, and this formula tells you that if that energy barrier that you put there is around 40 to 60 kT, then you would get something like a number of years to retain that state, okay? And this is how people design magnetic memory. They try to make that barrier as high as possible, increase that tau naught, and then they tell you, okay, if you leave your data here, it's gonna be here at least for 10, 20 years. Now, if you believe that formula, it's the thing with exponentials is, if you make the energy barrier around a kT or so, then you see that you get this really interesting picture where you are kind of predicting that this magnet will switch back and forth because this energy barrier can't deal with the the intrinsic noise in the system. Now, this formula, this way of thinking isn't quite true, because as you decrease the barrier, you kind of lose the idea of this red and blue state, but it gives you an idea that as you decrease this energy barrier, you can really get into this regime where you're fluctuating even if you're not doing anything. Now, we have this device this audience needs no introduction to this device, but we have this device that's called magnetic tunnel junction, which really turns those fluctuations into magnetic fluctuations into resistance fluctuations, okay? Depending on the orientation of your magnets. If you fix one of your magnets, for example, you can get these resistance fluctuations. And this is a very curious thing, that you can have a two-terminal resistance that's just sitting there at room temperature, and you're looking at its resistance as a function of time, and you would see that this resistance is changing its state by a factor of 2 or 3, even if you're not doing anything. And this can be picoseconds to nanoseconds, depending on the magnet design. Okay, that's very intriguing, because this is going to be a very useful building block for a qubit, where you're really getting the most expensive random number generation for free. Now, this is real, and we have collaborators, Professor Shunsuke Fukami and Professor Ono, for example, are experts in controllably making these stochastic magnetic tunnel junctions. And you're seeing on the top right here, different types of stochastic resistances. This is the most curious thing, that in the lab, you take this two-terminal resistance and just looking at it, at its resistance as a function of time, and it's doing these fluctuations. Okay, it's very well known to magneticians and experts in MTJs, but this is really the key computational building block that enables a very compact and efficient p-bit. Now, there are some very recent developments. If you're in this field, let me mention those, that, you know, this nanosecond operation of stochastic magnetic tunnel junctions, we've been predicting this for a number of years. We have a couple of papers that predicted that these magnets can be really, really fast. However, until recently, this was only a theoretical prediction, but Chris Safransky and Jonathan Sun, actually earlier this year, have shown that this nanosecond fluctuations in stochastic magnetic tunnel junctions is real. And very closely following that, or around the same time, in physical review, Professor Fukami and Professor Ono have shown the same thing, that really you can get these extremely fast fluctuations in nanomagnets. And another recent development came from our lab, which is, you know, you can make these magnetic tunnel junctions, in fact, doubly free, which is with no fixed layers at all, which is a very unorthodox, a terrible memory device, because it's really fluctuating all over. And we've put together some arguments and proposed that can actually be even a better p-bit for our use. So this is a very active field, with some of the major, you know, world-leading labs, experimental labs, being interested in this field. So you can see that this is very interesting and active. Okay, so however, I've been telling you a lot about this resistance fluctuation, but remember, we need an electrical device at the end of the day. That I need to have something that's electrically relating the input, analog input, to the output probability. So how do we do that? Well, we turn to STT-MRAM. Okay, this is this memory technology that's been scaled up to billion-bit units, and this is this really remarkable technology that's being developed, that has been developed by these major players. There are many others: Everspin, Samsung, Global Foundries. There are others. Intel is in this, and so on. Okay, and the idea is, you have one of these magnetic tunnel junctions that's connected to a transistor, and then you have these bit lines and a word line, so you can read and write to this magnetic tunnel junction electrically. And this is very interesting and one of the most promising developing and emerging memories for different types of on-chip memory applications. Now, we don't want to do memory, so we want to build a p-bit. So how do you make a p-bit? Well, maybe the most obvious thing to do is to replace the nominally stable MTJ with one of these unstable ones, okay? And preferably one of the faster ones that was like fluctuating with nanosecond timescales or something, okay? And then what you do is you put two more transistors. This is an inverter here, but it's really two more transistors, an NMOS and a PMOS to this thing, so that you get this really compact 3-transistor 1 MTJ device, rather circuit. And you get, if you simulate this in SPICE with, you know, taking the Berkeley models for the transistors and then using some of these sophisticated stochastic LLG models, and then you see something like as a function of the analog input, now it's become the transistor voltage, you get this fluctuating output that's approximately giving you the ideal behavioral equations. Now, it turns out, if you look at this carefully, you'll see that they're not quite the same. For example, you're not seeing rail-to-rail voltages at all ranges. So it's a little bit like this mean field idea, if you're familiar with how that works in this Monte Carlo simulations. But it turns out these fluctuations are a function of how well you design the inverter here and how well the MTJ is fluctuating between these two resistance states. This is a moderate parameter selection. It can look a little bit more like the ideal equations, and it turns out it doesn't have to be completely ideal when you go to these system level simulations. Okay, so we've built this device. We have a prototype, with collaboration, with our collaboration with Tohoku University. They basically provided us these stochastic MTJs, and we essentially built that circuit that I showed you earlier with a source resistance to sort of control, because we didn't have access to FinFETs. So you have to use these discrete transistors, and we added a source resistance here. Otherwise, it's pretty much the same circuit. And indeed, we've seen this controllable fluctuation at the output with analog inputs, okay? And here you're seeing these millisecond fluctuations, because we rather worked with these slow ones in the beginning. But as I said, these fluctuations can be at the order of, nanoseconds or so, which is very important if you're trying to solve a, probabilistic problem quickly. So this is our chip. You see that a PCB with 8 of these MTJs, but it's really the same architecture I'd shown you earlier, that these MTJ-based P-bits are really talking to one another through a microcontroller here, which was selected due to the experimental ease. And then it's a programmable synapse. It really connects these two different, these 8 P-bits to one another. Okay, so this was a prototype, and as I said, it's really the same architecture for all of the problems that we've solved. So what do you do with this? Well, this is a natural energy minimizer. This naturally implements things like simulated annealing and energy minimization. So we took this algorithm from the field of adiabatic quantum computing, which was like, okay, let's solve this factorization problem. It really is a generic optimization problem. Okay, so this algorithm in particular, if you're coming from the computer science field, this algorithm isn't necessarily a competitive algorithm to solve very large numbers, but it is really a generic optimization problem. And the fact that it's so generic is really its advantage. Okay, and here you have this factor f you're trying to factor, and these are the x and y are the factors you're looking for. So let's say x is a semi-prime, and the idea is when xy is equal to f, which is a factor which is a number that you provide, then this energy is minimized, and anything else really makes this energy larger. So you write this in binary, and then you turn this into a feedback formula, which is by taking the derivative of the energy with respect to the inputs only once. This isn't a difficult step. And then you set this up, and you, like in any experiment, you calibrate your system where the 8 p-bits are really uncorrelated. In the beginning, they're not talking to each other, and you get these equal probabilities for these factors. Okay, and once you do this calibration, you turn on the device and you take a time average of, let's say, 20 seconds or so, and then you see the correct factors of a number. In this case, it's, let's say, 945, come up with very high probability. Okay, so this is a probabilistic system. So in order for you to kind of measure something, you need to take some time average, and it really gets you to the right problem. So this was just a generic demonstration of how the thermal noise in the MTJ is turned into some useful computation. And the key idea is how cheaply it comes. You really harvested the intrinsic noise in the system without ever running a random number generator or anything like that. Now, let me quickly, in the beginning of the talk, I mentioned this factorization as inverse multiplication. Now, this is a circuit that, if you're familiar with digital design, this is a very familiar circuit for multiplication. This is the school book multiplication, where you multiply bits one by one, and then you kind of add what you get at individual layers. So this really is a circuit that multiplies two numbers, okay, 2 4-bit numbers to be precise. Now, what you can do with p-bits is that you can use this as a multiplier. You can really specify a's and b's, and that's going to multiply numbers. But of course, we've got very good multipliers. If you talk to experts in VLSI, they'll tell you that the CMOS multipliers are really operating almost close to as ideal as they can operate. So the key thing is, how about inverse multiplication or factorization? Now, if you build this circuit with p-bits, it turns out you can do the reverse, which is you can specify a product here, and you can get numbers. You can let the circuit evolve, self-organize to the correct answers. Okay, and this, it turns out this is a much better factorization algorithm. And just to give you an example, you can factor numbers that are almost, you know, these 32 bits numbers, which are in the billions. And the circuit, if you do the simulated annealing, is a function of time. As you slowly cool the system electrically, you get to these correct factors. Now, just to kind of give you an idea of how this works, this still isn't cryptographically relevant. So this isn't really a number that would break the RSA or that would be cryptographically important. But as a comparison to other icing machines, this is very large, okay? This is the largest number that we've seen in the literature. So it kind of shows you how this invertible logic idea can be very useful. And this is a fairly large system with 2200 qubits. It's got a huge phase space of 2 to the 2200. And so it's a fairly difficult problem, but in terms of factorization, it's probably not relevant. This is just to show how this our approach with, this was an FPGA implementation, really solves these difficult optimization problems. And in fact, this is milliseconds to solution, and we think that it can be nanoseconds with this if you build these circuits with MRAM. Okay, so that's really kind of to give you an idea and reference to how we're doing. Now, another interesting development, which we haven't published yet, is the idea of, again, a fundamentally important problem in computer science is this 3-SAT problem, the satisfiability problem, where you try to come up with a satisfying assignment in a complicated Boolean circuit. And invertible logic is very well suited to sort of represent these problems. And here we compared the results of our FPGA to the world's best SAT solvers in software. Okay, so these are some of the winners from the SAT-22 competition: KISSAT, Plingeling, and Crypto, it's CryptoSat, etc., YALSAT, etc. And we saw that if you want, you know, if you're okay with 95% accuracy, then even at the FPGA level, this P computer outperforms the best possible SAT solvers. Okay, again, this is just to give you an idea of the types of systems we can solve. This is up to 5,000 qubits, and these are extremely good SAT solvers that people have optimized over the years. I must mention, however, that if you insist on solving the SAT problem exactly, if you need the 100% accuracy, absolute ground truth, then it turns out our simulated annealing algorithm doesn't do as well. So we really can get to approximate answers very fast, and we can beat even approximate SAT solvers. But if you insist on the 100% solution, then our solver isn't very good. It's an algorithm related problem rather than the hardware. But I'll just mention that the approximate solutions are more than okay. And in fact, in real life, it's very rare that you need the absolute ground state of an optimization problem. 95% is more than okay, and we seem to be doing very well in that regard. Okay, so in the last few minutes, I'll just very quickly tell you that we've also spent some time on emulating quantum annealing with qubits. Okay, and this is not an idea due to us. This has been known in software for some time, but the fact that you can take D-Wave system and really scale it up in hardware and solve it much faster is an intriguing possibility. Okay, and the key idea is that there's this class of problems that are called sign problem free, and these systems, that includes the D-Wave system, can really be emulated by qubits. And this is just the details of the simulation is not very important, but it's just that this is the average spin of a quantum system, which is solved exactly and with this p-bit approach. And if you average the probabilistic result around 100 times or so, these are red dots are each single samples from our probabilistic sampler, they really fall on top of the exact quantum solution. Now, it's important to note that people talk about simulated annealing and this D-Wave approach. They're not the same. Okay, sometimes there's this idea that, D-Wave is really solving the simulated annealing problem. That's really not true. That the D-Wave is solving a quantum annealing problem. And here the probabilistic system is solving the simulated quantum annealing problem. So here's a legitimate quantum problem that's being solved by this probabilistic system. Okay, so the green dashed line here really is the quantum Boltzmann law, where you diagonalize a 2 to the n by 2 to the n quantum Hamiltonian. Okay, and so an intriguing thing is this SQA shows great promise in classical computers. So if you accelerate it greatly with p-bits, that really can become a competitive optimization solver. That's very important. And SQA, just to repeat again this important point, is different from quantum annealing. Okay, so we've solved up to 250 qubit problems in FPGAs. And the key point to note here is, if you take the 1 gigabit MRAM and make it into this 1 megabit qubit emulator, then you can really do what D-Wave does in a much bigger scale at room temperature. Okay, so this is the key point about why scalability of p-bits is so important. Now, in these last two slides, in the last 2 minutes or so, I'll just show you a comparison or a detailed understanding of why we think this good hardware for p-bits are important. Now, I've shown you this MTJ-based p-bit that gave you a complex functionality. Now, the first question you may have asked is, okay, how do I do it with CMOS? Well, MTJ seems like this exotic emerging technology. Even though it's been, scaled up to 1 billion bit densities, you might say that, okay, why do I not do this with CMOS? Now, you can, and we've done it. And with CMOS, the easiest way or the cheapest way to generate random numbers is to go to pseudo-random numbers. And one pseudo-random number generator is this linear feedback shift register. Okay, so if you don't know what that is, doesn't matter. It's just a very simple shift register with a bunch of XORs. Okay, and that tends to generate these random looking signals. Now, the thing is, it takes a lot of transistors. Even the cheapest, least sophisticated random number generator requires maybe 1,200 transistors or so, while the system that we showed here is only 3 transistors and an MTJ. And of course, the related power consumption increases. And here's a very conservative analysis that shows at least an order of magnitude difference. The reason in generating a random number, the LFSR is at least 10x greater than the p-bit. Now, the reason I said it's conservative is because no parasitics, no clock power, no clock routing, anything is included in that analysis. And in fact, we didn't even include the 10H or the comparator powers. So it's likely that you pay much more to generate a random bit compared to the MTJ. And more importantly, the LFSR is a pseudo-random number generator, which kind of repeats itself. So it's kind of a problem when you're solving very big problems, because then you're oscillating and you're not really random. Okay, so that's the key point about this MTJ-based device. However, I must mention that there may be analog ways of generating random numbers, even in CMOS, which might be comparable to the MTJ. Though, having the ability to put billion bits as random numbers in a chip integrated with CMOS, that's really the ultimate vision, which seems very hard to beat. Okay, so finally, this is my final slide. I'll tell you a little bit about the architecture level comparison, that it is not just that we have a good random number generator. Okay, this point is very important, that the architecture we have allows this thing that I mentioned in the beginning, that this massive parallelism. Now, how do you measure what's the key metric for a P computer? Well, the key metric is this number of informed flips per second. You want to flip as much as you can, but you want it to be informed. Remember, in the beginning, I mentioned that this feedback time is important because you don't want these random shouting, but you want this deliberate flipping of each p-bit with up-to-date information from their neighbors. Now, how many flips do you need for a problem? Well, that's very problem dependent. So there are generally 2 metrics, which is one of the ideas is the computational complexity of the problem. For example, if you have an MP problem, if you have a problem in MP, then as a function of the size of the problem, you may see an exponential increase. So you may need an exponential number of flips with increasing input size. but there's always a prefactor depending on your architecture. Okay, that's the tau knot. That's where the P computer can really help. And just to calibrate you, state-of-the-art performance from papers from Google, and I can share these references, are around 10 flips per nanosecond. This is what we can do in highly idealized situations where you can parallelize the updating mechanisms and so on. And this is really 10 flips per nanosecond. This is less than 10 flips per nanosecond. Now, if you have 1 million p-bits, each flipping at a nanosecond or so, which has been experimentally demonstrated, then you can have 1 million flips per nanosecond. So that's a 5 order of magnitude improvement in this massively parallel architecture. Okay, so this is really the key to why this MTJ in this parallel architecture can be really helpful. And let me just mention that we can reach 100 flips per nanosecond in FPGAs today, but that's really pushing the limits of what can be done in digital FPGA implementations. So you may ask, okay, why not 1 billion p-bits? Because it is true that people have integrated this device to this MRAM to billion bit densities. Well, I mean, that of course, the devil is in the details, and we think there are lots of walls to surmount in that case, but this is something that we're currently working on. So let me finish up by saying that we've been looking at different p-bit implementations. I've talked to you about this new and emerging paradigm in between deterministic and quantum computing, which is probabilistic computing with p-bits. And there is this intriguing idea of reaching this beating classical computers, and I've shown you some visions on how that can be done. And finally, in terms of what applications can be solved by p-bits, they're the really naturally stochastic ones, okay? And machine learning and optimization are full of these examples for which p-bits are a very natural fit. With that, I'd like to conclude, and thank you very much for your attention.